We are talking about the absorption of light of visible region by a non-metal. We have talked about the absorption of light by metal. Metals generally absorbs whole of the light to transfer its electron from the valence band to the conduction band. As because there is actually no band gap between valence band and conduction band in metals, so metals can absorb the all the energies of the light to transfer them. Actually, them means to transfer the electrons from the valence band to conduction band. But in case of semiconductors or in case of non-metals, the scenario is different. In case of non-metals, there exists a definite band gap between valence band and the conduction band. There exists a definite band gap. It may be small or it may be large. The band gap may be small or the band gap may be large. We had explained what is the band and what are the band gaps. We had explained it earlier. So in case of non-metals, there is a definite band gap. It may be a small. In the case of semiconductor, it is a small. And in case of insulator, it is large. The band gap is large. So the light energy is not sufficient to reach the valence band electron to the conduction band. That means the energy of light is not sufficient to reach the valence band electron to the conduction band in case of insulators. But in case of semiconductors, it is sufficient. It is sufficient in case of semiconductors. Now, sufficient means, say for example, silicon. Say if we take the example of silicon, it has a band gap of about 1.1 electron volt. 1.1 electron volt. Now, in the visible region, the light of the visible region, it has several waves associated with several energies. You know, in the visible region, we have several waves. We have violet wave, we have indigo wave, we have red wave, we have yellow wave. So it has a span of energy. It has a span of energy from 1.8 to say about 3.2 electron volt. It has a span. So in the visible light of the visible region has energy from 1.8 electron volt to 3.2 electron volt. So if the band gap lies up to 3.2 electron volt, then the energy of visible light is absorbed by the non-metals. If the band gap is above 3.2 electron volt, say for example, the band gap of diamond is about 5 electron volt. So it cannot absorb the energies. It means the electrons in the valence band cannot absorb the light energy, visible light energy. Because visible light energy has energy up to 3.2 electron volt. But say, say for example, cadmium sulfide, it has a band gap of 2.4 electron volt. So it will absorb, or the electrons of the valence band of cadmium sulfide will absorb energy of the light of visible region which are above 2.4 electron volt. Which are below 2.4 electron volt, it will not be absorbed by the electrons of the cadmium sulfide. So the energy above 2.4 electron volt, that means 2.4 to 3.2 electron volt, will be absorbed by the cadmium sulfide electrons. But the energies of 1.8 to 2.4 electron volt, the waves will not be absorbed by cadmium sulfide. It will be transmitted, and we shall see the color of that waves only. We shall see the color of that waves only. Which waves? That has energy, that have energy 1.8 to 2.4 electron volt. Now, now in case of silicon, what will happen? It is, the band gap is 1.1 electron volt. So visible lights of all energy of the visible region will be absorbed by the silicon because it has a band gap of 1.1. You are giving energy 1.8 to 3.2 electron volt. So all the electrons from the silicon valence band will be transferred to the conduction band by absorbing the light, because light energy, because the band gap is small. Because the band gap is small. So all the light energies will be absorbed. So if all the light energies will be absorbed, then what will be the color? All the energies will be absorbed. Then the color will be black. So pure silicon, you will find the color black. And find the color black because all the energies will be absorbed. No waves will be transmitted. No waves will be transmitted. So you'll see it as a black color. And if you see that no energies are absorbed, in case of silicon, all energies are absorbed. And in case of diamond, no energies are absorbed. So you will find diamond is colorless. So in one extreme, you will find the color is black. In another extreme, you will find it colorless. In between, you will see different types of colors, depending on absorption and transmission. So this is the partial absorption theory of partial absorption. This is the theory of partial absorption. In case of metals, you will see the full absorption. And in case of non-metals, you may see the full absorption, or you may see the partial absorption, or you may see the full transmission. Transmission means allowing the whole light to pass through the medium. That is called transmission. So in case of nanometals, you will find all three phenomena as absorption or transmission, full absorption or full transmission, or partial absorption and partial transmission. In case of partial absorption and partial transmission, you will find the color of the sample. Okay, it is clear? কোনো কোয়েশ্চেন আছে? কোনো জায়গা বোঝা নাই আমাকে বলো। কোনো জায়গা না বুঝে থাকলে বলতে পারো, কিন্তু জিনিসটাকে একেবারে মাথার ভেতরে ঢুকিয়ে ফেলো। এখন তারপর আমরা অন্য জায়গায় চলে যাব। ওকে ওকে, আশা করি তোমরা সবাই বুঝেছ। So this is again optical properties of metals. This is reflection, how light is reflected. Actually the light is reflected. This is absorption. Say for example, this is valence band and this is conduction band. By absorbing light, it goes from valence band to conduction band, and when it returns, it radiates light, it radiates energy as wave, and we see at reflection. We see as reflection. That is a common thing. We find it in the metal. Now, the color of non-metals. How can we find the color of non-metal? We explained it. We explained it just before. If there is partial absorption, you'll find the color. If there is partial absorption, you'll find the color. For example of cadmium sulfide, the band gap is 2.4 electron volt. So it absorbs the higher energy visible light, that is blue and violet. That means higher energy visible light means 2.4 and above, up to 3.2. These lights are blue and violet, and it will emit, it will transmit the lower energy lights, which are red, yellow, red oblique yellow oblique orange, and you will find a mixture of red, yellow, orange color in case of cadmium sulfide. In case of cadmium sulfide. Now, there is another phenomena can occur in case of, say for example, aluminum oxide. In case of aluminum oxide, it is called sapphire. Sapphire is a kind of jewel. If you mix some chromium oxide with sapphire with aluminum oxide, it is called ruby. You have many of you have seen the ruby crystal. তোমরা কেউ দেখেছো? Have you seen ruby? রুবি কেউ দেখেছো? রুবি ক্রিস্টাল আংটি পরে, প্রান্ত দেখো না?
হাতে পড়তে দেখছি স্যার।
হ্যাঁ, প্রান্ত তো তুমি তো দেখবেই। আর কেউ হাতে পড়ো রুবি ক্রিস্টাল? কেউ হাতে পড়েছো? That is ruby. রুবি ক্রিস্টালটা হচ্ছে is a very brilliant red colored crystal. Actually, it is aluminum oxide. It is mainly aluminum oxide mixed with some small amount of chromium oxide. Say say 0.5%, 0.5% chromium oxide. The band gap of aluminum oxide is high. It is actually insulator. Just like insulator, the band gap is high. But the band gap of chromium oxide is small. So valence band, conduction band of, say this is valence band and this is conduction band of aluminum oxide, is high, large, above 3.2 electron volt. So visible light, it do not absorb the visible light. It transmits the visible light. So aluminum oxide is colorless. Now, if you add chromium as impurity here, then extra one band is appeared here due to chromium, because the band gap of chromium is like that. This is band gap of aluminum oxide, and this is band gap of, say, chromium oxide. So you will find a band gap here. For that, there is a transition. There is a transition of electron from here to here, or from here to here and here to here, with absorbing your visible region energies. That means about 1.8 to 3.2, whatever it may be, by absorbing the visible region energies. Actually, the red color of your ruby is for the chromium oxide, which is impurity. So if you mix impurity, say for example diamond is colorless, and if you mix impurity, if you can mix impurity in the diamond, you can get color of the diamond. The impurity, what type of impurity? Which have band gap in the region of 1.8 to 3.2 electron volt. This type of impurity. Not a band gap of high impurity, or not a band gap of low impurity. If you mix a impurity of band gap, of small band gap, then all the light will be absorbed by this. You will find it a black colored. But if you dope an impurity of the visible region band gap, that means 1.8 to 3.2 electron volt band gap, then you will find a color. In ruby, the chromium oxide is the impurity. The chromium oxide is the impurity, and you find the color. You find the color, red color of the ruby is for impurity, not for aluminum oxide. So this is another phenomena. It is very good. It is very important phenomena. If you see sapphire aluminum oxide and 0.5 to 2% chromium oxide. Sapphire is colorless because its band gap is greater than 3.1 electron volt. Adding chromium oxide, you will find a band between this band gap. Alters the band gap, and chromium oxide absorbs blue light, is absorbed, yellow green light is absorbed, and only red color is transmitted. What is the result? Ruby is deep red in colored. You'll get deep red colored. You see, this is the sapphire. This is the above one is sapphire. No absorption. No absorption. You see here, no absorption. But in case of ruby, you see here, there is an absorption and there is an absorption also. Absorption means absorption of light, absorption of light of the visible region, absorption of wave of the visible region. You will see there is an absorption. Here is an absorption and here is an absorption. What is a blue light is absorbed, yellow green light is absorbed. That is, blue light is absorbed, yellow green light is absorbed. So red, only red is transmitted. So you will find find the color of red. You see here it is VIBGR. This is colored region. It is VIBGR. Up to this it is absorbed. Up to this it is absorbed. From here to here it is absorbed. And this is transmitted. And you will see the color of ruby is like it. Up to this is absorbed. Here this is absorption and this is absorption. Up to this is absorbed. So this is the color of nonmetals. This is the color of nonmetals. Now, another property of light, which is called refraction. Which is called refraction. What is refraction? What is refraction? You see here this picture. See this picture. Light is coming through this way. This is a prism. This is a prism. And here light is bending. Light is bending. And you will find light in this way. You will find light in this way. Light is coming this way. If it is transmitted straight, you can find the light in this way. You will find the light in this way if it is transmitted. But now it is going in this way by bending it. If you dip a stick in the water, you will see this phenomena. তুমি পানের ভিতরে একটা যদি লাঠি ডুবাও, তাহলে কি হবে? লাঠিটা কেমন দেখবে তুমি? It is bent. It is bent. That phenomena, that bending of light is known as your refraction. Now, refraction means your intensity of transmitted light, what called intensity of transmitted light, decreases with the distance traveled. Or what is actually the refraction? The refraction is the path of the light is changing. The light is going in this way. Here is a medium, here is another medium. Say, for example, this is air, and this is glass, and say this is glass, and say this is glass. The path of the light is changing. The path of the light is changing. This is called refraction. Now, why refraction occurs? Why refraction occurs? You know, light is an electromagnetic wave. Electricity, electric field, and magnetic field. Light has electric field and magnetic field perpendicular to each other. Now, when it passes through the atom here, when it passes through the atom, it makes the atom as dipole. The electron cloud of the atom distorted. The electron cloud of the atom, light distorts the electron cloud of the atom. What do you mean by distortion? Distortion means the electron cloud is homogeneous in all the ways. But the electron cloud is now like this. It is called distortion. It is not homogeneous. So you will find a dipole here. You will find that, say, for example, here the concentration of electron cloud is higher than here or here. You'll find concentration of electron cloud is higher than here. So you will find a dipole here, positive charge and negatively charged, whatever it might be. Whatever it may be, but the electron cloud is distorted. Now, for this distortion, or to distort electron cloud, the energy of light, some energy of light is lost. Some energy of light is lost. So the speed of light becomes slower. So what is the result? Light is slower in material versus spectrum. In vacuum, the speed of light is, for example, 3 into 10 to the power 10 meter per second. But if light passes through a material, it has to do some work. It has to do some work with the atoms or with the molecules of that material. What work? It distorts the electron cloud of the atom or molecule of the material. And for that, it loses some of its energy and it becomes slower. So the index of refraction means the speed of light in a vacuum and divided by speed of light in a material. So speed of light in vacuum is always higher, and the speed of light in a material is lower than speed of light in the vacuum. You'll see some examples here. If you see the lead glass, the index of refraction is 2.1. If you see the silica glass, it is 1.46. And if you see in case of quartz, it is 1.55. These are the index of refraction. That means in case of lead glass, light travels more and more slowly because it is 2.1. So intensity of the transmitted light decreases with the distance traveled. Oh, that is another thing. If the thickness of the material is higher, then light have to encounter more and more atoms because the thickness is higher. So light have to encounter more and more atoms. So its speed becomes slower to slower. So intensity of the transmitted light decreases with the distance traveled. That means thick pieces is less transparent. That means thick materials is less transparent compared to thin pieces. It is because light have to do more work. Light have to do more work. So this is the refraction. Refraction means the slowing of the speed of the light, as well as bending of the direction of the light. Bending of the direction of the light. Now we have seen the absorption of the light. We have seen the reflection of the light. We have seen the refraction of the light, and we have seen the transmission of the light. Now, another thing, a small thing, it is the diffraction of the light. I have told about it in the first or second class that if there are boundaries, if there are grain boundaries, light diffracted from the grain boundary. Light diffracted from the grain boundary. Say, for example, I have to go to the তোমরা দেখতে পাচ্ছ? This is a polycrystalline substance. Say, for example, this is grain boundaries. This is grain boundaries. ঠিক মতো দেখা যাচ্ছে তো, তাই না?
Yes, sir.
হ্যাঁ। So when light falls, say this is the light. When light falls here in the grain boundary, it is diffracted in the grain boundary, and it comes here, say for example. Then it is diffracted again, comes here, and it is diffracted again, comes here, and it is diffracted again, comes here. Or it may comes here to here. Or it may come, light falls here, it may comes here. Or it may diffract it again to here. So some of the light can be lost by the diffraction. You see, this light is transmitting, this light is transmitting, but all other light is lost by diffraction. It is diffracting here and here and here. It is entirely the diffraction is within the system, but some light is transmitting. So if this is a large polycrystalline substance, if this is a large polycrystalline substance, if this is a large polycrystalline substance, more and more light can be lost by diffraction. Say, more and more light can be lost by diffraction. It is going from here to here, from here to here, from here to here, from here to here. It is the light contained in the system itself, although there is no absorption. There is no absorption. But due to diffraction in the grain boundaries, it remains within the system. One or two light can be transmitted, but maximum of light due to diffraction is contained in the system, or all of light can be contained in the system if it is a strong, if it is a large polycrystalline substance. That property is known as diffraction of light. That property is known as diffraction of light. So we have seen the reflection, we have seen the reflection, we have seen the refraction, we have seen the diffraction, we have seen the absorption, we have seen the absorption. In absorption, you have seen the partial and full. And last, we have seen the transmission. Transmission of light. We have seen all these things. Every phenomena can be occur simultaneously, or it can occur individually, it can occur individually. All light can be transmitted, or all light can be reflected, or all light can be absorbed, or every phenomena can be occurred simultaneously. Now, these are the actually theory of light. Theory of light means interaction of light with material. Interaction of light with materials. Of light with material. Now, we will discuss the optoelectronic instruments rather. Optoelectronic instruments. What are they? Optoelectronic instrument means the instrument that is prepared by optical properties of material. That means the interaction of light with material. That is called optoelectronic instruments. The instruments which are prepared by optical properties. That is the application. Application of optical properties of light. These are the application of optical properties of light. These are the applications of optical properties of light. There are a few instruments. There are many instruments, not a few. There are many instruments like luminescence. Luminescence. 3 to photoconductivity. Number 3 is solar cells. Number 4 is your optical fibers. Number 5 is your laser. And the number 6 is LCDs. We shall discuss luminescence. Let's see and see. Actually, luminescence. See, and please correct the spelling of luminescence. LCD. So, what are they? That means if you prepare an instrument with the phenomena of luminescence, that is one kind of optoelectronic instruments. We find it in our tube lights, and we can find it in our televisions. Televisions means that old style televisions which have cathode ray tube. তোমরা টেলিভিশন দেখো না, এত বড় মোটা লম্বা একটা টেলিভিশন ছিল আগেকার দিনের টেলিভিশন গুলো। এখন তো ফ্ল্যাট স্ক্রিন এসছে। আগে টেলিভিশন গুলো, আগে কম্পিউটার গুলো কিরকম ছিল, বিশাল পিছনে একটা লম্বা জিনিস ছিল। দ্যাট ইজ ওই স্ক্রিনটা is prepared on the theory of luminescence. It is very simple. Luminescence theory, it is very simple. If a substance, if a material, say this is a material, light falls on that materials, it excites the electron of the material from valence band to conduction band, and when the electron returns to the valence band again, it radiates light, and we see here the light. That is called luminescence. So this luminescence is of two types. One is fluorescence, FLUORESCENCE. Another was another is phosphorescence. One is fluorescence and another one is phosphorescence. What's the difference? In case of fluorescence, the absorption and the emission, that means the absorption of electron and the return of electron occurs within a very short time in case of fluorescence. And in case of phosphorescence, it occurs with some delay. With some delay. So it is phosphorescence. I think তোমরা এটা ফিজিক্যাল কেমিস্ট্রিতে পড়েছো, তাই না?
জি স্যার,
হ্যাঁ,
অর্গানিকও ছিল স্যার।
হ্যাঁ, এটা পড়েছো। So we found it in the fluorescent light. Fluorescent light means what is fluorescent light? বলো তো কোনটা ছিল? Fluorescent, what is fluorescent light? কোনটা ছিল? Tube light. Tube light is one kind of fluorescent light. Fluorescent light. কি হয় ওটাতে? কি হয় ওটাতে? A mercury lamp. A mercury lamp. Say for example, this is a mercury lamp. It radiates light. It radiates light in the fluorescent tube. Fluorescent tube টা আছে. You will get a fluorescent tube here. Say for example, this is fluorescent tube and দেখা যাচ্ছে? This is fluorescent tube. Say for example, this is a fluorescent tube. This is a fluorescent tube. And here is some fluorescent substances. There is a layer of fluorescent substance. Here is a layer of fluorescent substance. This is a layer of fluorescent substance. A mercury light here supplies the light to the fluorescent substance. So what happens? The atoms of this fluorescent substance, the electrons of the atoms of this fluorescent substance goes from valence band to conduction band and then returns, then it radiates the light. And we are seeing this light. We are seeing this light. এই যে মার্কারি ল্যাম্পটা আছে, এই মার্কারি ল্যাম্পটা অ্যাকচুয়ালি কোথায় থাকে? এই মার্কারি ল্যাম্প একটা ভালো অ্যামাউন্ট অফ ইলেকট্রিসিটি উই ক্যান রিকোয়ার। এই টিউবলাইটটা প্রথমে স্টার্ট করতে একটা ভালো অ্যামাউন্ট অফ এনার্জি লাগে। হোয়াই টু লাইট দ্য মার্কারি ল্যাম্প। স্টার্টিং কি হয়? ওই মার্কারি ল্যাম্পটাকে জ্বালাতে হয়। ওই মার্কারি ল্যাম্পটা কি করে? সে লাইট রেডিয়েট করে। কি লাইট রেডিয়েট করে ওই মার্কারি ল্যাম্পটা? ইট ইজ জেনারেলি ইউভি লাইট। ওই ইউভি লাইটটা গিয়ে কি করে? ওই ইউভি লাইটটাই হচ্ছে অ্যাকচুয়াল কাজ করে। কি করে? ওই ফ্লোরোসেন্ট সাবস্টেন্সে তোমার গিয়ে হিট করে। And the electrons from that fluorescent substance jumps from valence band to conduction band and then returns. After returning, it radiates lights also, and we will see the white light. That is the fluorescent light, and that is called luminescence. That is called luminescence. What is the process? Here is the process. Electron jumps from the lower level to higher level, and when it returns, re-emission occurs, and you'll get the emitted light as your fluorescent light. Now, Now, the second one is called photoconductivity. Photoconductivity. This is another type of theory that is called photoconductivity. By this photoconductivity, we can prepare some types of photodetectors. Now, what is photoconductivity? For that, we have to know about the semiconductor again. We have to know about the semiconductor. So in the semiconductor, let us see about the semiconductor again. Say, for example, this is a silicon crystal. For example, this is a silicon crystal. You see silicon in the outermost orbit of silicon. How many electrons are there? Kata? Silicon and outermost orbit kata ase?
4টা sir.
4 electrons. 4 electrons. So say for example, this is a silicon. It has 4 electrons, 1, 2, 3, 4, and it shares another 4 electrons with another silicon atom, another 4 silicon atoms. তোমরা এই সিলিকনের স্ট্রাকচারটা বুঝতে পারছো? সবাই দেখো, এটা যদি না বুঝো তা আসলে কিছুই বুঝবে না। সিলিকনের স্ট্রাকচারটা বুঝতে পারছো? Say this is silicon. হ্যাঁ, সিলিকনের 4টা, একটা সে 1 2 3 4, আবার সে আর 4টা কি করছে, আর 4 জনের সাথে is sharing another 4 electrons with other 4 silicon atoms. So it makes 8 electrons of each silicon atom. And silicon is a semiconductor. Its band gap is about 1.1 electron volt. It is a semiconductor. It has a very small band gap. Very good. Now, if we dope a phosphorus atom in between it, if we dope a phosphorus atom in between the silicon atoms, what will happen? Phosphorus atom has 5 electrons in its outermost orbit. So, of them, 4 electrons are shared by 4 silicon atoms with its vicinity. And you see this gray color electron. This is the 5th electron. Phosphorus have 5 electron in its outermost orbit. Among these 5 electrons, it it shares 4 electrons with 4 silicon atoms in the vicinity of it. And the 5th electron, this is the 5th electron, it is here. And actually, it becomes free. It is not bonded with any other atom here. It is not bonded. So it becomes, actually, it becomes free. So this free electron can easily go from the valence band of this system to the conduction band of this system. This free electron can easily go. It is free. It is not bonded with any atom. It is not bonded with any atom. So it is free and it can jump to the conduction band very easily. For this electron, there is no band gap actually, or a very small band gap for this electron because it is free. But for these electrons, the band gap is about 1.1 electron volt. But for this electron is actually there is no band gap or a very, very small band gap. So this electron can jump to the conduction band very easily and make a semiconductor a conductor and make a semiconductor to conductor very easily because by jumping by jumping this electron from the valence band to the conduction band. So this type of doping makes a semiconductor to the extrinsic semiconductor. If there is no doping, say for example, this is silicon, there is no doping, there is no impurity. This type of semiconductor is known as intrinsic semiconductor. And if it is doped like it, if it is doped with say phosphorus, then it is called extrinsic semiconductor. And it is called n-type semiconductor. N means negative. Negative means there is an extra electron here, so it is negative, and this is called n-type semiconductor. Now, if we dope the boron here, what will happen? If we dope boron here, what will happen? In the boron, there are 3 electrons in the outermost orbit. So it can share 3 electrons with 3 other silicon atoms. It can share 3 electrons with 3 silicon atoms, but it cannot share any electron with this silicon atom. So there is a deficiency of electron. There is a deficiency of electron here, and we call it a hole. Hole, H-O-L-E, hole, because there is a deficiency of electron here. So there is a extra electron, there is an extra electron here, and there is a deficiency of electron here. Deficiency of electron means positive charge. So it is called p-type semiconductor, p-type extrinsic semiconductor due to doping. Now, this electron can move easily from valence band to conduction band, or from here to here, here to here. This electron can move easily. And this hole also can move easily. How? This hole also can move easily. because you see there is a hole. There is a hole. Say for example, we come here actually. There is a hole. For example, one electron from here comes here. এখানে একটা electron ফাঁকা. So one electron from here can come here. So now hole is where? Here is the hole. And from here an electron come here. So hole is here. From here an electron come here. So hole is here. From here an electron come here. So hole is here. So hole can move. An electron can move as well as a hole can move. Now, hole will move the opposite direction of the electron. Say, for example, an electron comes here. So, direction of electron is from here to here. And direction of hole is from here to here. So, the direction of hole, the movement of hole, the direction of the movement of hole is opposite to the direction of the movement of electron. এটা মনে আছে? এগুলো মনে আছে সবার? কি হলো বলো, মনে আছে নাকি এটা নতুন পড়ছো মনে হচ্ছে?
অল্প অল্প স্যার।
অল্প অল্প মনে আছে, তার মানে মনে নাই। অল্প মনে থাকা মানে হচ্ছে মনে নেই। হ্যাঁ, এই অথচ এই প্রশ্নটার জন্য তোমরা পাগল হয়ে গেছিলা, স্যার এই ইলেকট্রিক্যাল প্রপার্টি থেকে তো প্রশ্ন করেন নাই, হ্যাঁ এই প্রশ্নটা স্যার আনসার করতে না পেরে আমাদের মানে পরীক্ষাটাই খারাপ হয়ে গেল, তাই না? হ্যাঁ, ম্যাটেরিয়াল সায়েন্স পরীক্ষাটা কেন খারাপ হয়েছিল? স্যার আপনি ইলেকট্রিক্যাল প্রপার্টি থেকে একটা প্রশ্ন দেন নাই, এটা একটা কথা হইতে পারে স্যার, হ্যাঁ আমাদের পরীক্ষাটাই খারাপ হয়ে গেল। হ্যাঁ, এখন দেখছি আসলে এটা দিলেও তোমাদের পরীক্ষাটা খারাপ হতো। হ্যাঁ, so the movement of electron and the movement of hole, the movement of hole is opposite to the movement of electron. এটা বুঝতে পারছো তো? জিনিসটা বুঝেছো কিনা আমাকে বলো, না বুঝলে আমি আগাতে পারবো না কিন্তু কিছুতেই। এটা বুঝে গেছো হোল কি, ইলেকট্রন কি, এন টাইপ কি, পি টাইপ কি, and movement of hole and the movement of electron. কারো কোনো কনফিউশন থাকলে আমাকে জিজ্ঞাসা করো। এন টাইপ কি, পি টাইপ কি, হোল কি, ইলেকট্রন কি, and the movement of hole and electron. এগুলো বোঝা গেছে? এই 6টা জিনিস বোঝা গেছে? এগুলো ভুললে চলবে না। কি বলো রাফিউল, বুঝেছো তুমি?
জি স্যার, জি স্যার।
বেশ, ভেরি গুড। কামরুল? হ্যাঁ কামরুল, দেখছো তার ভিডিও নাই, সে নাই। তারপরে ওই যখন পার্সেন্টেজ দিতে আসবো তখন বলবে স্যার আমার ইন্টারনেটটা একটু ঝামেলা করতেছিল, স্যার আমি এরকম, আমি ছিলাম স্যার সারাদিন ক্লাসে কিন্তু নাই। তুমি কোথায় গেছিলা কামরুল?
স্যার কল আসছিল স্যার,
সর্বনাশ।
কেটে দিয়েছিলাম, আবার আসছে, আবার দিয়েছে কলের জন্য দোষ।
এখন তুমি বুঝছো হোল কি?
জি স্যার।
হ্যাঁ
জি স্যার।
হ্যাঁ, ইলেকট্রন কি বুঝেছো?
জি স্যার।
মুভমেন্ট অফ হোল কোন দিকে হবে, ইলেকট্রনের দিকে না বিপরীত দিকে?
বিপরীত দিকে।
বিপরীত দিকে। তাহলে কারেন্ট কোন দিকে পাবো আমি?
স্যার
হোল মুভ করছে, আমি কারেন্ট কোন দিকে পাবো?
অপোজিট দিকে।
হোল মুভ করলে কারেন্ট অপোজিট দিকে পাবো, আর ইলেকট্রন মুভ করলে কারেন্ট কোন দিকে পাবো?
ইলেকট্রন মুভ করলে অপোজিট দিকে, হোল মুভ করলে
কারেন্ট কোন দিকে যেদিকে হোল মুভ করবে সেদিকে কারেন্ট পাবে।
জি স্যার।
এটা ইজি ব্যাপার,
স্যার।
বুঝতে পারছো তোমরা
জি।
সবাই? যে যদি ইলেকট্রন মুভ করে, we'll find the current opposite to the direction of electron. But if hole moves, we'll find current to the direction of the movement of the hole. Now, if hole appears, then it is p-type semiconductor. After doping, if hole appears, it is a p-type semiconductor. And after doping, electron appears, it is n-type semiconductor. বুঝতে পেরেছো এটা? হ্যাঁ, আমরা এর বেশি ডিটেলসে যাব না। আমরা এখন এবার আরেকটু ইয়েতে যাই, আরেকটু ডিপে যাই। এগুলো তোমাদের পড়ানো হয়েছিল, তবু আবার পড়াচ্ছি। আরেকটু ডিপে যাই। Let us consider a p-n junction. Say, for example, this is p-zone, p-type semiconductor, and here is n-type semiconductor. So, in p-type semiconductor, you will find holes. Say, for example, these are the holes. And in n-type semiconductor, say, for example, this is n-type semiconductor, you will find electrons. This is a p-n junction. p-n junction means this is p-type semiconductor and this is n-type semiconductor. We mixed it together, so it is called p-n junction. আচ্ছা, আমাকে একটু বলো তো, এই যে p-type semiconductor, p-type semiconductor I have shown the holes only. এখানে আর কি আছে? Holes means hole মানে hole কার hole থাকবে? Say, for example, you have doped boron. You can dope aluminum. That is all the +3. This is p-type, and say in the n-type, you can dope phosphorus, you can dope antimony, which have +5 state. So, what do you mean by doping? Doping means there are another substances, there is another substance, and you have inserted small amount of other substance. So, this is a p-type semiconductor. This means that here it is full of silicons, and you have doped some, say, for example, boron here. You have doped 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You have doped 12 borons. For that, you got 12 holes. Here in this site, you have doped 12 phosphorus. You have doped 12 phosphorus. For that, you got 12 extra electrons. But there are enormous amount of silicons also. the main substrate, the main thing is silicon. You doped this side 12 boron and you doped this side 12 phosphorus. But there are say 1,000 atoms of silicon. So I'm showing only the doped substances, not the actual substrate, not the actual mother substrate. Say, for example, the mother substrate is silicon. Now, what will happen if we connect a p-type semiconductor with an n-type semiconductor? What will happen? This electron will come to the hole, because hole means electron deficient space. Hole, what do you mean by hole? Hole means electron deficient space. And these are the extra electrons. So these electrons will come to the hole and will make this hole filled. Will make this hole filled. Then if one electron entered in the hole, there will be no hole. There will be no hole. Now, boron has 3 electrons in the outermost orbit. It is actually neutral, isn't it? It is actually neutral. There is we are telling that there is a hole. Why? Compared with silicon, it has 1 electron less. Actually, it do not have any electron less. It is neutral. But compared with silicon, it has 1 electron less. So we called it a hole. Now, if 1 electron enters here, boron will have 4 electrons. Then this boron will be negatively charged actually. This boron will be negatively charged. So if electron enters here, then this side will be negatively charged. This side will be negatively charged. Now, from the phosphorus, you'll see that phosphorus have 5 electrons. Phosphorus have 5 electrons. It is neutral. 5 electrons in the outermost orbit, so it is neutral. We are telling that phosphorus has 1 extra electron. Comparing with silicon of its vicinity, actually it do not have any extra electron. It has 1 extra electron compared to the silicon with its vicinity. So if this electron of phosphorus goes to the boron, then this phosphorus will lose 1 electron and this phosphorus will become positively charged. So this side becomes positively charged and this side becomes negatively charged. So if we draw it again, we'll find 3 holes, say for example 3 holes and 3 electrons. Three holes and 3 electrons, and a negative charge region here, and a negative charge region here, and a positive charge region here. Negative charge region here and the positive charge region here. So now this electron will also try to come here. This electron will also try to come here to fill the hole, but it cannot, because if it comes here, this negative charge will repel this electron and it will go back. If it comes here, this negative charge will repel it and it will go back. It will go back. So there is a region where, say for example, this and this and this side is negative, this side is negative, and this side is positive. This side is positive. And here electrons are there, and here holes. So now electrons are not coming to this side and holes are not coming to this side, because holes will try to come here and this positive charge will repel the hole here. So this region, in this region here, there are no holes and no electrons. Only silicon atoms are here. In this region, there are no holes, no electrons, only silicon atoms are here. This is called depletion zone. This is called depletion zone. Now what will happen? We have connected a p-type. We have connected a p-type with an n-type semiconductor, and now we found a depletion zone. Here it is positive, and here it is negative. Now, here you will find a potential barrier. What is potential barrier? Because due to this barrier, one electron cannot come from this side to this side. And due to this barrier, a hole cannot come to this side to this side. That is called a potential barrier. In the depletion region, you will find a potential barrier. There are electrons, there are electrons, and there are holes. But no hole can enter in this side, and no electron come in this side. Why? Because of your this barrier in the depletion region. This barrier, because of this barrier. Now, what will happen if I connect a battery here? This is positive charge. This is positive charge, and this is negative charge. We call it forward bias. We call it forward bias. What will happen? Here, this is electron. So electron will flow this side, and this electron, when it come here, it will repel this electron. That means this electron will give energy to these electrons. And this positive charge will give energy to these positive charges to go in this side, and this electron will give energy to go in this side. Now, this is a barrier. This is a potential barrier. For example, if the substrate is silicon, the potential barrier is 0.7 volt. The substrate is silicon, the potential barrier is 0.7 volt. Now, if the energy of the battery is higher than 0.7 volt, is greater than 0.7 volt, then the electron will break the barrier, will overcome the barrier, and from this side the electron enter this side, and from this side it will go again in this side. And this hole also will overcome the barrier and enter in this side. So if you connect a battery here, whose energy is greater than this potential barrier, then these electrons will pass through this potential barrier, will break the barrier and go to this side. Why? Because this electrons will give energy to these electrons, and this electron will overcome this barrier, the barrier of this. That is called your PN junction or diode. That is called PN junction or diode. And this is called forward bias. What do you mean by forward bias? The negative side is with N type and the positive side with P type. That is called forward bias. Now, what will happen in the case of reverse bias? We'll discuss it tomorrow.